So probably this happens to be the last technical session of this program. Afternoon we have a briefing by Professor Allen on the program, and then we will be having the feedback from your side, and then the valedictory. So that's afternoon. We meet for a consolidation by Professor Allen, and then a feedback by you, and a valedictory between 3:30 and 4. That's the program. So this session, I would be presenting the uh, research work from our group directly to 2 3 research programs from our group, which contains all the topics we discussed over the days, which contains some specific aspects of the matrix. In the first class, we said of what is a matrix, what is reinforcement, when matrix is changed, what happens, when reinforcement is changed, what happens, how the characterization protocols are being executed, etc., etc. So this in this work, so I'll be focusing on some composites based on polylactic acid initially, and then subsequently we will be moving to some other matrices we have experimented in our laboratory. So this work is primarily, our target is to do energy saving. So energy sector is one of the targets of our research group. Biomedical applications is a second target of our group. Catalysis is another target of our group. Definitely catalysis involves energy saving also. So this is extensively all over the world, in different parts of the world, left hand side in India, in different parts of the world, in Kerala too, we have many research groups who focus on biological systems and biocomposite systems. So these biocomposites have by now grown into a very very big area of research, because the spectrum of matrices available, as we discussed, the spectrum of reinforcements available for us, infinite large number of combinations depending upon your interest and depending upon the application. We can have multiple combinations. When you make a floral carpet, multiple flowers are there. Any type of flower can be combined to make the garland. So it's your option, your imagination, and it's your contribution. So I will be initially beginning with a matrix, a beautiful bioplastic matrix called polylactic acid. When we have learned in our deform L form, light deflect deform L form, the first example of particularly active compounds, we learn of a molecule called lactic acid, which contains two functional groups. A carbon atom is there, a carbon atom is there, a carbon atom is there, carbon atom is connected to a CS3 group down, it is connected to a hydrogen, and it is connected to two functional groups. One is OH group and the other one is acidic group. So carboxylic group of one first molecule can condense with the hydroxyl group of the second molecule. We know that when a carboxylic group is condensed with the hydroxyl group, an ester is formed. COOH plus OH is equal to condensate. HOH will be removed, will be having an ester removed. When the ester groups are repeated multiple times, the product is known as polyester. And only one ester is there. When two molecules condense, it is an ester. When dimerization happens, trimerization happens, tetramerization happens, polymerization happens, the large number of ester groups will be formed in the big structure. It's a polar structure. C double bond O, carbon oxygen electronegativity difference is there. The polarity is there in the molecule. You call it as a polyester molecule. So it's a polyester. Nature has a very interesting aspect, very interesting look into the fabrication, the making of this polylactic acid. Many of the plants we have seen, cornstarch, tapioca roots, chips of starch, etc., etc., we can derive this polylactic acid. Now in the laboratory, therefore, since polylactic acid is available plenty in nature, many of the large groups in the world, nature works, V4U, Evonik, Total Cobium, Sinbra, all these companies are highly involved in the business of polylactic acid because polylactic acid is a wonderful matrix. Many research students like you, many of the people like you work on this field to form as a biodegradable matrix, and its food contact is acceptable. So food industry is the preferred candidate, and good optical properties because you the clarity. When you see through the film, you can see the other side. Perfect clarity is there. So because of this good processability, you can process it into any dimension, any shape you want. So it is a very interesting product. If you look into the chemistry, we have to meet the growing demands of polylactic acid. We said that it is obtained from nature, but in addition to that, we can make polylactic acid in the laboratory. How do we do? You take a left hand, so you take a left hand lactic acid molecule which contains two functional groups, OH group and carboxylic group. Do a polycondensation just like the reaction. OH reaction, that's called condensation. When water molecule is eliminated, reaction is called condensation. And multiple times condensation happens, you call it as polycondensation. When you do a polycondensation reaction, you will be getting low molecular weight polylactic acid having a molecular weight is kilodalton, means that is atomic mass unit only. So you'll be getting low molecular weight. But people want to have high molecular weight. Therefore, they do another procedure. Low molecular weight polylactic acid is subjected to low molecular polylactic subjected to depolymerization procedure to convert it into a cyclic form. So in the cyclic form of the ester is called lactide. Now the ester group is not open. Ester group is made into a ring. Such a ring we make with the ester group. You call it as a lactide. Lactide, you can cut the ring. That's called ring opening polymerization, ROP. So make a lactide and cut the ring. So you'll be having again functional group opened. So when you do that, ring opening is very easy. You can have extensive polymerization. Degree of polymerization will be enhanced significantly. You'll be having a high molecular weight PLA. So depending upon our requirements, sometimes we may need polylactic acid of low molecular mass. So you stop there. If you want to have high polylactic acid product, you will be going for further steps. So that's it. So you can go up to a molecular weight of 10 lakhs even, depending upon your requirement. So properties, the most interesting aspect is I said you that it's a transparent film. So you can add another ingredient into that so that you can make it a blend. Any polymer can be received. It's a very good front. So any polymer can be mixed with it. And any filler can be added, any reinforcement can be added, meaning development of a blend with another polymer or development of a composite with any type of reinforcement is possible with polylactic acid because of its excellent processability. Therefore, extensively it is being employed for a large number of applications. I'm sorry for this small font sizes. I can read that industrial applications, biomedical applications, agricultural applications, large number of domestic applications are there for polylactic acid. So now, if you ask me for some literature, if you ask me some literature, you can read this literature. So a lot of, I have given this literature, material science and engineering, applied biological materials. These are beautiful descriptions of polylactic acid. If you want, tempting us to start work on that. Actually, these reports tempted us to work on polylactic acid because they said these reports say that polylactic acid processing is very beautiful and it is worth doing that. If you have a target application for catalysis, you can use, for biomedical application, you can use. So all these reports, you can see that. I will leave the slides to you. If someone is interested, you can read these slides. Definitely it will support your projects and research programs. So this is first part of the work we have started. This is done by my PhD student in Rarima. She is in Emirates now, working as a faculty. This job involves, we have utilized polylactic acid for a catalytic operation by incorporation of silver nanoparticles into that. We have made an in situ generation of silver nanoparticles in presence of polylactic acid. So silver is a good catalyst. Silver is a good catalyst. But the efficiency of the catalyst is lesser if the catalyst particles agglomerate. Particles should be spreaded. Particles should be spreaded. When particles are spreaded, the advantage is that the surface area is increased. When surface area is increased, more and more reaction molecules can anchor on its surface, so that reaction kinetics can be enhanced. Thermodynamically also reaction can be favored. So thermodynamic and kinetic supports are being activated if you spread the silver nanoparticles. For spreading the silver nanoparticles uniformly, we are using PLA. Even without PLA, the reactions can be executed. But with PLA, the reaction efficiency increases significantly. So that is being justified through this work. So the job is to make polylactic acid containing silver nanoparticles, and which is used for a reduction procedure, standard reduction procedure, nitrophenol conversion, paranitrophenol to paraminophenol conversion. So we made the catalytic system, catalyst containing PL matrix, and which is tried for a catalytic reaction to justify that, to confirm that in presence of PLA, the reduction procedure happens more efficiently. So that's the consolidation of the report I am going to present. So this is if you look into that carefully, lactic acid is there, polylactic acid is there, left hand side green, silver nitrate is there, and that we are going to embed silver nitrate into polylactic acid matrix to make sure that silver is in the zero oxidation state. So we are using the reducing agent, glucose as a reducing agent. So when silver nitrate gets deposited, charge will be there. Glucose will be helping us to nullify the charge. And then it is executed in alkaline medium, NaOH. The efficiency is enhanced in alkaline medium. So if you look into the right hand side, polylactic acid shown in the green color, and upon which silver is embedded in the neutral state. And the byproducts of this reaction are an acid gluconic acid, sodium nitrate, NaNO3 and H2O. That will be, all the impurities will be readily dissolving in. That's the advantage of this technique. All the impurities will be going into the aqueous phase, which can be perfectly separated from the organic phase. The organic phase contains PLA with the silver particles. So by the end of the job you do, getting two layers. One is organic layer. Organic layer contains our polylactic acid and silver. Aqueous layer contains all the impurities. So the impurities removal is perfectly easy in this strategy. And we have made different compositions of PLA. First column PLA, second column is silver nitrate, amount of silver nitrate. So silver nitrate dissociation is quantitative. AgNO3 gives Ag plus NO3. So molar concentration, so the ratio is 1:1:1. Therefore, whatever molar ratio of AgNO3 taken, that is the molar composition of silver also. So 1:1:1. So first one contains no silver nitrate, which is written as P0S. Second one contains 10% of silver nitrate, is called P10S, because 10 means indicate how much of silver percent. 20 is there. 30 is the maximum composition we have used. We tried for making a P40S system, but agglomeration probabilities, because when particles, filler particles are more in number, they will get agglomerated. So the homogeneous distribution will be questioned. Therefore, we do not have the ultimate mileage by the end of the day. So we stopped at that composition. And this, how do we know that? How do we know that this PLA now is enriched with or embedded with silver? For that, how do we know that it is uniformly distributed? Here is the significance of the experimental protocols we have learned, UV visible, IR, etc., etc. We have done an experiment for UV visible experiment. In a suitable solvent, we have kept polylactic acid, silver. We have kept silver. Left hand side is silver without PLA. Silver without PLA. So without PLA, so the system contains a solvent and the silver particle. I said that silver particles have the catalytic activity, which can be enhanced by PLA. This is the first evidence for that. Without PLA, if you look into that, absorbance on y-axis and wavelength on x-axis immediately you realize that it is a U visible spectrum. How do you know that it's a U visible spectrum? Yeah, absorbance should be on the y-axis and wavelength is. And how many hills are there? Two hills are there. Two hills are there means we have only one particle there, silver only in the solvent. But two hills are there. What does it mean? Each hill is a representation of something, some transition. Two transitions are happening there. It means silver is in two states. Means silver, somewhere silver is agglomerated, sometimes silver is not agglomerated. So that's a clear-cut indication. If it's just on the right, if you look into the right-hand side, it is with PLA. If there's only one hill, what does it indicate? Only one absorption happens in the system, means system is not heterogeneous, system is homogeneous because only one signal, one pulse is generated in the system. When you have more and more pulses generated, that shows heterogeneity within the system. Only a single signal, that's the first confirmation that with a solvent, if the system is homogeneous or heterogeneous, we can execute the usable absorption. The absorption is uniform, we having only one signal. So that's the first evidence we got that PLA helps, that reinforced our concept that PLA. So what is the job of PLA? PLA helps to reduce the agglomeration and make the big silver particle uniform within the system so that you will be having better catalytic activity, right? Then the second one is we looked into composition of P10S, P20S, second graph, and the P30S, P10, P20, P30. All of them give, the P10 means what is the composition? All of them are with the P, all of them give only single signal. All of them give only single signal. But slightly, when the PLA amount increases, slight redshift happens because initially when 10% of the system P10S was scanned, 405 nanometer was the pulse. Then the pulse increased slightly, 408, no significant, but then 420 was there. So all of them gives only single signal, means that all of them have uniform distribution of the particles within the medium. Done? Do you understand that concept? Then we have to scan it for, we have to go for further examinations because we do not believe in, just like a clinical doctor scanning our body for different diseases. So only doctor is not happy with a single experiment. Doctors can do pressure is examined, temperature is examined, right? Only a scientist comes to the conclusion of a result only with different experiments. First we went for UV visible, so that showed that yes, your sample is uniform. And what else? Then we have made this student was very intelligent, Darima. She said that, sir, we can do a special technique called to generate porosity so that. See, she made a beautiful technique. This technique contains, if more pores are there in the film, more pores are there, they are the pockets where the reactants can anchor more effectively. So she wanted to make the PLA silver system with more pores. So for that she intelligently made, she says a reported technique, but she made it beautifully for that. Initially, left hand side, she made a film. She made a polylactic, was dissolved in suitable solvent. So after that, she spreaded it over a base. So that is film is made. That's the film, and that film was solvent was there. Initially, solvent was not dried. With the solvent, she made the film on that. Then she kept it in a humid system. Humid system means atmosphere contains lot of water. Humid system. Now what two processes operate? The solvent present along with the polymer will go out. Solvent present in the solvent will try to go out because it will try to vaporize. When the solvent is exposed, it will vaporize. Then in the humid atmosphere contains water. It will try to come down. So when the solvent comes out, someone goes out and someone comes in. So water gets in the second process. You can see that solvent in the medium tries to go out and the other one was condensed. So beautifully, when solvent leaves out, you will be having beautiful pores in the, that's actually water entered, water occupied system. Someone leaves, it's an intrinsic rearrangement happens in the system. Then so all those spots are being occupied by water now. No solvent is there. Now carefully, if you heat that, now only water is there. Some remaining solvent could be there. If you carefully heat to 70 degrees centigrade carefully, slowly water will be, you will be getting a beautiful morphology. So this technique is called breath figure technique, BFT, breath figure technique, to make porous films. We cannot do it with another technique. This is a molecular engineering, because pores are being generated by small molecules only. Some molecules go out, so rearrangement happens within the system. So pores are intrinsically generated. We can do it. It does not need sophistication. Only a humid environment is sufficient. On a cold day, very cold day, rainy day, if you do that, you will be getting that, right? Then this is a beautiful technique proposed in 82. It's an old technique, but even now people use it. And so now she has made a beautiful porous film. We have to now go for those who be confirmations. Confirmation. How many confirmations we have to go? So we do not believe science. We are not happy with one result. First result told that, U visible told that yes, it is uniformly distributed. Secondly, we have done this, the film, it is made into a beautiful film based on the first observation. Now we go for different examination. Left hand side result is called X-ray. Exactly. How did you know that X-ray is X-ray? Intensity versus 2 theta is plotted. That is the way you said it perfectly. The moment you say, you should know that it's what spectrum it is shown. So since the graph contains intensity on y-axis and 2 theta on X, it's an X-ray. You can see that. PLA's, PLA's theta, if you read down, PLA should be having a 2 theta value 16.4 and 19 degree. And silver should be having a 2 theta value of 38.3, 44.5, 64.8. These are in reports. In old literature tells that if you use PLA, that pulse will be there. If you use silver, that pulse will be there. If you look at all the three graphs, all these pulses are there. It means that the system you developed definitely contains PLA and silver. Because if silver is not there, 38.3 pulse will not be there. 38.3 pulse can be read there. Similarly, if PLA is absolute 2 theta 16.4, all the signals contain 16.4 degree signal, and the other one 38. There it means confirm that system you made is definitely a combination of, it's a composite system, combination of silver as well as PLA. Then another beautiful technique is called XPS. What is that XPS? X-ray photoelectron spectroscopy. It XPS, you call it as XPS. XPS will tell you the binding energy. There are two components. How the binding happens between the two components. There you have to look into signals. You can see right hand side, if you look into that, two signals you can see. That signals XPS, in fact, I have not explained the previous examination, but believe me, it's a very powerful technique to find out if a metal is present, its oxidation state. Its oxidation state can be whether it is in the plus oxidation, just one oxidation state, plus 2 oxidation state, etc. You can easily find. Two signals will be there. This has happened through different types of peaks. We classify the peaks as silver 3D peaks, 3D peaks, and 3D half 1/2 peaks, etc. This is a simple technique, but since we do not have time, we do not explain. These two signals and the difference between electron volt is plotted on y-axis. That's called binding energy. Where does the signal appear and what is the distance between the signal? What is the distance between the signals in an XPS will tell you that whether silver is in the 0 oxidation state or +1 oxidation state. The literature tells us that if the pulses in XPS is 6 electron volt away, definitely the metal is in the 0 oxidation state. Exactly, we got a result like that. The splitting difference, you can read the splitting difference of the peak 6 electron volt confirms that the non-ionic state of silver. Silver is not in ionized form, it is in 0th oxidation state. Done. It's a beautiful exercise. I wanted to have some more explanation. If someone is interested, we can have a discussion later, but since this is only a complementary examination, I do not explain it further. So then the next examination, how does, if I enter into the system, this is called morphology. This image is known as a scanning electron microscopic image with a specific in all scanning electron microscopic images you will be seeing into means called magnification, means how many times our eyes cannot see that, A film is showing how many times into 5,000 or into 5K it is written that the image you are seeing is actually 5,000 divided by, if you want to get the dimension, actual dimension, divide this dimensions marked by 5,000. Then only you will be getting, actually, it could be in nano dimensions. So you can see that. So beautifully, that's the first 10 system, 20 system, 10 system, 20 system, and 30 system. So percentage of silver percent. So if you look in the middle part, that's the perfect system. Most of the pores are having uniform sizes, etc. Left hand side is slightly overlapping. Right hand side is perfectly overlapping because right hand there is overloading of silver. Left hand side is not reaching the threshold value. Sufficient silver is not there in the first system. Right hand side more silver is there, but the second system is exactly optimized system. So if you control this, the effect of concentration. So if you control the concentration, you can control the morphology of system, and that beautiful structures, the reactant molecules can anchor reactor. So that system contains silver as well as polylactic acid. So it's a polymer supported catalyst. Silver is the catalyst, but that its efficiency is significantly enhanced by everywhere we have silver spreaded, and the incoming molecules also can be fitted into the molecules conveniently. So this is a just when you can have using transmission electron microscopic images, distributions can be found. You can find the particle just by the technique I said you. The particles are distributed. Magnification is written on the left hand side. So if you divide that number with the using a scale, how many particles are there? One particle dimension you can measure, and divided by 500, you can measure the dimension. And when you do that dimension, all the particle size reach about around nanometer dimension. So 8.71 in 10 raised to my plus or minus 0.34 is the dimension average size of silver particle distributed within the system. And EDAX is an expedition. What is called EDAX? Elemental detection. Elemental detection. You want to confirm that copper should not be there in the graph because I have not used copper. Gold should not be there because all these are contaminations. Whether my system contains only silver, what are the elements we present? Polylactic acid contains only carbon, hydrogen, and oxygen. Silver contains only silver. So only these signals should be there. If other signals are there, your product is contaminated. So if you look into that specifically, you can see that carbon is there, carbon is shown, oxygen is there, silver is there. Only silver is there. Mean that is the most contamination part. Other things we know that the element we used is only silver is a major part. No other element is found in this. Only silver signal is there. It means that, and silver quantity is 0.99, and that is exactly matching with the amount of silver we have used initially started for the experiment. So it confirms that quantitatively the experimental protocols were correct, and the results obtained are. So you have developed this, all these examinations. We have done X-ray, we have done XPS, we have done SEM, we have done UV visible spectroscopy. I think that they have done IR also, that is not incorporated in this graph. All these experimentations, so just like an advocate arguing in presence of a judge. Science always when we present data, people should be having confident evidences should be there. So with that, when she presented before me, sir, I argue before you, I made this composite system, I agreed. So this is then she used it for and another examination she did is, up to what time, what are the phase transitions? This is another technique. I explain to this, what is the thermal analysis and mechanical properties analysis. Thermal analysis indicates there are, if what is the, up to what temperature a system will be stable, that is called a thermogravimetric analysis. If there are any phase transitions will happen during our catalytic activity, that is called DSC, differential scaling calorimetry. Phase transitions are examined by DSC, and glass transitions, crystallizations, all these are observed with the DSC. But the other one with TGA will help us at what temperature material will be used. But catalytic activity normally, because when a catalytic system temperature will be, therefore temperature sensitivity would also, this temperature, the TGA curve I do not add it, I missed it. But DSC curve is very useful. From here I can obtain the glass transition first dip. This is a DSC. So how do you know it's a DSC curve? It's a heat flow is always in, and temperature always in. The temperature, when the temperature comes in x-axis, evident that it is a thermal analysis. And when you do that, you can see that first dip happens around can see that that's the first glass transition, that's the glass trans temperature. So for all the system, first dip happens around 60 degrees centigrade. So first small dip, only small dip will be there. First small dip is, if you compare with the slides yesterday gave you, crystallization, etc. Interestingly, you can see that this is having a process called crystallization, because there's a graph going up. This is crystallize the first down graph is endo, heat absorbing graph, and then another down graph is there, crystallization. But in between a graph goes up, that is called the second graph is melting, and the graph which goes up is called crystallization. So during crystallization system, it's a polymer system containing fillers. So there's a chance of filler particles will act as nucleus, and crystallization possibilities, nucleation procedures will be there. Crystallization. So all the systems respond to that. So there is system. The results are that this system will melt. The dip down is around 150 degrees Celsius. So ideally, you use this system below 150 for a catalytic reactivity below 150 degrees centigrade, because this system will melt at 150 degrees centigrade. Ideally, use for a catalytic operates at 100 degrees centigrade. It's okay. 110 is okay. 120 is, say 130, 140 will be dangerous, because system will be collapsing, because system matrix will melt. Don't do that. Similarly, glass trans temperature is 60 degrees centigrade. There also there is a probability for 60 glass trans. Ideally, this is good for in between for a reaction. 70 to 120 degrees centigrade will be the ideal catalytic range, where temperature range where you can utilize this system, right? Then, but it does no, glass transition will not be affected, but melting will be significant. Glass transition will not be affecting significantly. It will affect, but it will not be, but melting will definitely affect. And then we look another examination. So how many examinations we have done now? UV visible we have done, X-ray we have done, XPS we have done, morphology we have done. Then this the DSE we have done. Then the sixth examination is mechanical properties. So we can see that when silver particles are 1, 2, 3, 4, 4 systems are there. One without silver, other 3 systems with silver. You can see that the blue is the top one. Silver is anchoring onto there is another evidence. So alone PLA strength is very low, green graph. But the modulus of the system goes significantly up, almost 2 times, 2.5 times, because the silver is getting anchored, clutches the macromolecular system. So when you try to apply a deformative force, the silver and the chain, silver gets reinforced in the system very uniformly, as evidenced by UV. So the system is so strengthened, so very high modulus is being derived for the system. So it's another evidence. So sixth evidence for the development of the system. With all those background, we have started using a catalytic activity. Whether the system is with the catalyst, with the PLA and without PLA, you try that. So what the job is, your reactant is your weakness. So orthonitrophenol. How do you write that orthonitrophenol? One aromatic ring and a OH group and a NO2 group. Now our job is to convert NO2 group into NH2 group, nitrophenol to amino group. When aromatic OH, nothing happens to the OH group. Aromatic ring is there, OH group is there in the reactant and product, but NO2 group is reduced to, reduction is hydrogen, addition of hydrogen, replacement of oxygen hydrogen is called reduction. So if you look into the left, UV visible is again another wonderful technique to do that. Left graph, 2 UV spectra are shown. One with a small hill, other one with a big hill. But big hill is red shifted. Right side, big hill is red shifted. Stop there, look into that. And there is at 400 nanometer, at 300 nanometer, no hill is there. 300 nanometer, no hill is there. What is the product? What is our product? Para aminophenol. If aminophenol is there in the system, 300 signal should be there. Aminophenol, you can read literature. Aminophenol will give a spectra at 300. Do you have a signal at 300? You have a signal at 317, left one, and you have a signal at 400, but you do not have a signal at 300. Means product has not been formed with the silver. And the reducing agent is sodium borohydride. NaBH4 is the reactant is orthonitrophenol, and the reducing agent is sodium borohydride. The catalyst is silver or PLA supported silver. So reactants are paranitrophenol and NaBH4. Catalyst is silver either silver alone or silver with PLA. Done. So the evidences are in the UV visuals from our literature. We will see that if 317 is there, it's its reactant. If 317 signal is there, reactant. 300 signal is there, product, right? But this 300 signal is absent. 300 signal is absent. It means that the left-hand side is reactant only. Right-hand side is reactant with the sodium borohydride. Reactant with the sodium borohydride. When sodium borohydride is removed, the reaction, the reduction of 4-nitrophenolate ion formation, H plus reaction happen, but the actual product does not form. That is the indication. But if you look down, look to the second graph. The second graph also, that is with the PLA 10 and PLA 30. There also, you do not see a significant signal at 300. Means product has not been formed in. But if you look down, that is the catalytic activity reactant with the PLA, 20 PLA 20 percentage of that. See, 300 signals are there. Only in that graph where PLA 20 is used, 300 product signals are appearing in UV visible. In no other case, the first case and in the second case, no other signals are there, but no signal representing the reactant. This is from our literature knowledge that if 300 signal only is there, then only the product will be formed. 300 signal is formed only when PLA 20 is. It's lessons. Number one, silver alone will not be acting as a catalyst. Right hand side, these top figures. Even PLA supported silver, if it is not optimized, that will not work. Working of the catalyst will happen only at a specific composition, because only at a specific composition, uniform distribution of silver happens within the, sometimes silver will be very low, no catalytic activity. Sometimes silver will be extremely high, but agglomeration, no catalytic activity. But at a particular composition, you have, because between these two seats, if one boy comes and sit, one seat is vacant, that is not correct. If 3 boys come, the seat is again cannot be occupied. 2 boys come only, exactly the matrix will become continuous. This equation is ready for molecules. At a molecules, depending upon the free volumes, organization of catalyst happens, uniform happens only at specific compositions. At that composition, all the reactant molecules, maximum reactant molecules will be reacting with the catalytic surface. I will show you the mechanism and you will be having better product formation. You can look into the next, this is the mechanism. So that is the P20 substrate. Initially sodium borohydride will anchor on that. Sodium borohydride is the reducing agent, anchor on to that. Then paranitrophenol will anchor on that. Both of them, since the structure is porous as evident in morphology, so there is most probability that more probable matrix is generated where sodium borohydride can come very closer to the reactant, paranitrophenol. So that paranitrophenol gets reduced to paraminophenol, and that quantitative evidence can be obtained from an equation. Change in relative, so again visual evidence, change in relative absorbance can be computed from, this is very extensively used by researchers. This is called change in relative, so CRA at a time interval of 8 minutes is calculated by 77. You can see that for the second composition, 98% of absorbance change is there. That means that system is highly efficient to execute this catalytic activity. Another question that comes up, your catalyst is good. How many times in industry people use? Only your catalyst can only be used only once. Can you use it for multiple times? Then only industry will accept it. Yes, we tried it for 1, 2, 3, 4, 5, 6. 6, at least 4 cycles. 6 times without purification, just wash it thoroughly and then use it for further application. The very same efficiency is maintained for 4 cycles. After 4 cycles, slightly we have a reduction to 80% reduction. So after 4 cycles, because of the after 4 cycles, a lot of catalytic surface will be contaminated. So anchoring ports will be jammed. So therefore you cannot use it further. So there's another thing. I will quickly go for another work. I will have one more work is there. So this is again Rarima's work. In this work, we have not used a filler. This is an example of a blending system. These two polymers are blended, which can further be used as a matrix. I'm speaking only of a matrix now. So this matrix definitely, which can you can add silver into that. Can add a silver into that to make a better matrix. So this effort is primarily for this is not actually a composite system, it's a blend system where polylactic acid is blended with another biopolymer. So this is different depending upon the matrix nature, you can control the composite properties. So this is another evidence for the matrix properties modulation. If instead of single polymer PLA, if you use another polymer also, another biopolymer, gelatin. Gelatin is, our skin contains, normal skin contains a substance called collagen. Collagen. So collagen when boiled, you will be getting, with water, you will be getting a polymer called gelatin. So this gelatin is a beautiful substance. So this will make the substance. It is with the bread. PLA alone is bread, but bread with jam is PLA with the gelatin. So gelatin is a very soft material. So it is that will give that it's a hydrophilic material. That will be the excellent modulation of a matrix can be done by gelatin. Definitely after that you can reinforce it with a filler to make a composite system. This effort is only to modify the matrix. What she has done is PLA was mixed with the gelatin and she loaded a drug into that, metformin, which is used as a sugar. For diabetic patients it's given to them. So it's this job is how this matrix can be used as a carrier of a drug. So drug is being loaded into a matrix PLA plus gelatin. If we try with PLA alone, PLA definitely will do that, but efficiency has been enhanced multiple times in presence of gelatin. So PLA with gelatin, and then she loaded a drug into that, and she examined the drug release. That is the story. So how a modified PLA matrix can act as a drug carrier and drug releasing matrix. For this, so that's the job. So this is gelatin. So if you look into gelatin, it contains a large number of polar groups, C double bond O, NH, C double bond O, NH extensively. That polarity is beautiful because PLA is also polar. So polar interactions will lock the matrix. So that's the logic in selecting the components. Polylactic acid contains COO ester, say ester. It's plus charge minus charge. This is also plus charge minus charge. Polar interactions will anchor the substances together to make a beautiful matrix. So, right, you can have this detection with the help of IR. So when polylactic acid signature alone is taken, you will be getting a signal. When you will be having gelatin signal, you can take gelatin signal, but these signals will be shifted to right hand side if hydrogen bonding exists, and in the spectrum you can find out that whether hydrogen bonding exists. If the hydrogen bond shifting and widening of these signals happen, it shows that hydrogen bonding happens. Particularly with the system contains OH groups. So this is a the effort is to make a foam, FOAM, foam. Foams are soft, but they contain large number of pores. Foams are soft, they contain large pores. And into the pores, we can trap a drug. Into the pores, so this is PLA, this is gelatin. So when they combine together, I make a shell. I make a shell. And inside the shell, I can add a drug. So this is drug-loaded PLA gelatin matrix. At a particular pH, it will break. At a particular pH, drug will be breaking. So that the shell will be breaking, drug will be releasing. So because our body has the specific pH values at different points. That's the logic in the system. So this is the making of the matter. These tricks are they do not need sophistication. That is one of the we generally do, all our students do films with the simple techniques because it is fabrication is, but in the commercially they should be expanded. But basically we make a lot of simple strategies. So left hand side is PLA, right hand side is gelatin. We have dissolved it in trifluoroethanol. Trifluoroethanol, we have dissolved it. We made a beautiful solution, right? Into that solution, what we have done is, that's a solution now. Now we are adding this is a trick to generate pores. I said you another technique earlier, breath figure patterning for making pores. This is another trick to make forms without any sophistication. PLA is there, gelatin is there, dissolved up in a solvent, then slowly add methanol in. Methanol is a non-solvent. Now, there's a complexity, confusion generated within the system. Earlier, PLA and gelatin fully dissolved in the solution. They are happily living as a solution. Suddenly, someone falls on the head. Then there is a turbulence happens in the system. There is a competition happening between solvent and non-solvent. Trifluoroethanol is a solvent. PLA, then non-solvent comes. What is your role? You go out. You go out. So he pushes. Solubility decreases when the amount of CHOH increases, because non-solvent slowly increases in the medium. So the polymer becomes agitated. It becomes, oh, what is something? Something is there. I was living happily, but a non-solvent comes. I'm troubled now. He does not want to remain in this. Slowly he settles down. Slowly he settles. So settling down happens. The solvent molecules will escape. Solvent molecules settling down. Solvent molecules will be escaping from the medium. Wherever the solvent molecules from, that region will be hollow, and finally you will be getting a form there. What is a form there? Form is a solid system containing lot of pores inside, right? So using this small trick, you generate a soft system. It is not a gel, because gel should contain a solvent inside. When it is dried, it is the gel stage is over. You will be seeing a film. So this is a form, beautiful form. It contains lot of free spaces. I can definitely, if I put it into a drug, definitely drug will be getting into that. Right? There's another technique called positron live to annihilation spectroscopy, PLAS, by which we can find out how much of pores are there in the system. It's called porosity or void content in a system. So here also she made 4 systems. One system without gelatin called P0G, one system with 5% of gelatin. It is called P05G. G indicates gelatin. She made another system containing P means polylactic acid, 10G, then P15G. 4 systems are there. Out of this, the story says that out of this system, P10G system turns to be a good system after all the optimization protocols we have done. I will show you. Morphology was the most interesting thing. You can see that left hand side's morphology is 0 system, no gelatin. Right hand side is 5 gelatin. Down left is 10 gelatin, and down right is 15. And if you scan carefully that, a very accepted pores, etc., depending upon the drug dimension, etc., P10G happens to be more, from our other experimentations also, P10G seems to be, it contains a lot of uniformly distributed pores compared to other systems. You can see that. So she has made a cartoon based on that, which is written on the right hand side, showing that different PLA alone is there, gelatin is there. When they are combined, the other system, P10 system, is having, right hand side top is having a uniform morphology, right? So based on that, we defined a system, and you can evaluate that P, if you by TEM usual protocols, we can find out the porosity, etc. So you can there are other standard techniques find out the porosity. So the porosity has been found with P10 system. It contains 75% of pores are there within the system. So that's a good indication for us. And then standard protocols, structural analysis, IR is confirmed. IR confirms that PLA gelatin system. So IR of gelatin is given, IR of PLA is given. PLA signature, IR gelatin signatures are present in the red graph, which shows that PLA is there, gelatin is also there. Signals are not significantly shifted. It means that each one maintains its integrity, therefore it's a heterogeneous system. If PLA remains as such, gelatin remains. It's a system which contains PLA and gelatin, but they are separated. It's a heterogeneous system, but they will be functioning together. But if PLA gels into gelatin, functional group signatures will be broadened and shifted to right hand side. That does not happen. Then the X-ray evidences. X-ray evidence. All the old PLA is having signal, gelatin is having signal. The other one, but gelatin is having less signal, so that you can see that without gelatin the system is highly crystalline. Presently there are Schur equation, lot of calculations we can do for XRD. So from there you can see that without gelatin, PLA is 76% of crystalline. But with the introduction of gelatin, the crystallinity of the system tends to be more, so it tends to be amorphous in nature. And then we have done, so we have taken the water uptake. Water uptake is another examination, simple examination. So whether system is hydrophilic or not. So you can see that water uptake, right hand side, with the time, P10 system and P15 system takes more water. So system tends to be in a hydrophobic nature to the hydrophilics. You can measure contact angle also, whether it's system hydrophilic. Water absorption quantity is here, you can say that hydrophilicity has been increased. So this is a simple you can put it in water, and after 3 years you can measure how much of water is going into the system. So this is a simple examination. And then we have to check, most importantly, it's a biosystem. How do you know that biosystem is a biosystem? So you generate an ambience and you feed the material with an enzyme. A biosystem is expected to work without breaking during service time. But after service time, when the moment you put it in soil, as that soil pH and that humidity and the presence of enzyme there, it should, when it is operating, that enzyme is not there, so it is not degradable. But when you put it in environment, pH is set, humidity is set, enzyme is also set, that will act and kill the material. That's the concept of, people will ask me, if biocomposites are there, day one onwards, will they degrade? They will not degrade, because the enzyme is not there. The enzyme present in the soil is not there, water is not there, humidity, so it will stay. But the moment you put in soil, you are triggering the degradation activity, right? So with that, you can see that we have used, generally we have used an enzyme. So in the presence of the enzyme called trypsin, we have added, the matrix was subjected to, exposed to an enzyme called trypsin, and the soil ambience was given there, pH and pH was given and the humidity was given. At that time the material started degrading. You can see that over a period of time, degradation profiles are given there. Material significantly undergoes degradation, and degradation of P10, you can see that P10 happened 95% over a period of time. After 28 days, within 1 month time, this biocomposites, this biosystem, 98% of its weight is degraded within. You can see it's a simple experiment. Put it in soil, close it, and then after 20, take the weight. There's a simple experiment, soil degradation. Take a, bury it under soil, keep it 28, then take weight out. Then visually you can see that it is degraded. A lot of pores will be generated. So it's a simple experiment. And so the bacteria, enzyme, helps to degrade the system. So we confirm that material undergoes significant degradation, and that's a wonderful observation. Then we have the BET analysis is known for you. This is a Brunner Emmett Teller mechanism and the nitrogen adsorption mechanism. The two techniques, BET will tell you surface area and the pore dimensions. Pore dimensions, surface area, and the pore dimensions by nitrogen adsorption and for BET examinations. These are two protocols where you use pore dimensions. How much pores are there? Pores are there. And if the pore size is 2 to 50 nanometers, it's called meso. If the size of a pore is below 2 nanometers, it's a nanopore. 2 to 50 is mesopore. Above 50 nanometers, it's a macropore. So it's the values, all the values run between 2 to 50. Therefore, average, the system contains mesopores. So it's a porous system. That's why we said it as a foam. It's foam. It contains, it's a light substance containing large number of pores. And so the BET examinations tell that The surface areas are 6.48 and 9.48 respectively. And then we conducted the previous, Noel presented this examination. This is called cytotoxicity. You spread some spread cells on your matrix. And after some time, if the cells are dying, do not use it further, because it's evidence. This is mice cells, L929 lines, we call it L929 cells are spreaded on your system, and wait for that something happen. We can see that whether the cells die or not. The cells die, you will not see any image, but you can see the cell control sample. Compare, you have to control the control sample there, no? And your P10C, you can see that small cells. Even after many days of incubation, cells are alive. It's the first examination we do. Such cell distribution will not be there. You can compare with the P15 and P10. The structure is different, isn't it? So more cell proliferation happens on the matrix of P10. So it is a more biocompatible system. So that's it. First test, then we will be doing another test called hemolysis, etc., etc. And this is the drug release examination. The drug it's a comparison between simple PLA. Simple PLA is red graph, and gelatin modified PLA. P10 has been identified as best system. The black graph is gelatin modified PLA. She has loaded a drug, metformin hydrochloride, into that, and slowly at a specific pH value, she is trying to how much of drug is coming out. If you look into the red graph, suddenly the graph goes up to some quantity. The moment you start release, drug will come out. From which system? PLA alone. Then slowly, you can look into the red graph. But if you look into the black graph, it is not a sudden release. Slowly over a period of time, slowly it diffuses, and then final release is more black graph is above the red graph. Means over a period of time, higher release will be happening from gelatin loaded system, right? And that release is more consistent. Sudden release is not. If the drug is suddenly released into the body, activity will be less, but if slowly it is injected, activity will be higher uniformly. So it means that gelatin has an effective control. Gelatin is a good metrics for controlling the release profile of. So I have given a mechanism on the right hand side. What I said is shown as a picture on the right hand side, and that forms I think the conclusion. The conclusion from these two observations gave us the confidence that PLA can act as an efficient substrate for catalytic activity and bio drug release, capping agent, synthesis of silver nanoparticles with controlled size and morphology. And its second work shows that PLA could entrap gelatin in the fabrication of polymer forms. And the third key critical observation is that fabrication techniques like breath techniques and solvent induced technique can induce sufficient porosity in matrix. We have seen two techniques. The second one is called NIPS. The PLA based materials are flexible towards various applications ranging from industrial to biomedical applications. So it will serve you in energy sector, it will serve you in biomedical sector, it will serve in different fields. In future, the environmental awareness would initiate large scale implementation of PLA and when broaden its application either to unexplored area. If you don't mind, you can run down the slide, biocomposite slide 10. You are running now. Biocomposite 10. And I have, I have another application. I will complete it in 5 minutes time. This is, we have used these composite systems for making piezoelectric crystals. It's one of the major recent. Mecca is also working on piezoelectric systems. So piezoelectricity, you know that piezoelectricity is for working, piezoelectricity is a small, if you press, that's a mechanical force. If you press a polymer sample, electrical energy will be generated. Using that electrical energy, press electrical energy. Or electrical energy, if you give electrical energy, mechanical force will be good. That is called reverse piezoelectricity. electricity input is mechanical, output is electrical. Piezoelectricity input is electrical, output is mechanical, reverse. So some polymeric materials which are having polar nature. So when you press it, they will be having two effects. A tribo effect, tribo means friction effect will be there because of polar. And then other effect is orientation effect. So because of these two effects, you will be having tribo piezoelectricity generated. And this tribo piezoelectricity, through the, we do not have time to explain all these things. We have developed I had this is my student. Can you run the slide? Can you run the slide from there? So we have run down. So I had some more slides, but quickly I will send the slides to you since we do not have time. So you can run the slides. I can go to the last part of this. So what I said is given here, piezoelectric materials, etc. Large number of applications. So my student Shafiq has developed a ethylene vinyl acetate millable polyurethane MPU. So it's a blend system reinforced with nano hydroxyapatite. Please, Amrita, please run. And these are the characteristics. The characteristics I said you are same. Therefore, you will understand it very clearly. Yes, just a minute. This is polyurethane. Yesterday we visited a plant. That plant contains this reaction. You remember that? So it's millable polyurethane reaction. That's the, you have seen a resin is being injected. That is called polyurethane. So please run. Run. Please. Okay, so thermal analysis is there, mechanical strength evaluation is there, dynamic mechanic. You know the difference between mechanical analysis and dynamic analysis. You stretch a sample is kept to constant and stretch it. That's called static mechanical analysis. But if you subject a sample to a specific frequency, sample is dynamic. Sample is dynamic, and then the mechanical analysis is done. So it's called dynamic mechanical analysis. And the dynamic mechanics output is not elongation break, etc. etc. This tan delta damping, loss modulus divided by storage modulus. We do not have time to explain. Please proceed. Yeah. So we have justified that dielectric features should be measured for a piezoelectric material, and then run. And there is a we have Rafiq has made a piezoelectric material like that. No, he made a polyurethane EVA nanohydroxyapatite, which is nothing but bone. That's a pakka biocomposite, and that is sandwiched between two copper electrodes, and measure the dielectric constant, etc. And there is a technique called atomic force microscopy. So he made it with a beautiful strategy. This is the sandwich he made, and then run down. Run. So simply by touching that, current will be generated. So you can see that is his photograph. He has pasted that as he has made that film, and he pasted that film into this part. So if this is a patient, hospital bedridden patient, night time, he cannot call anyone will not, no one will be seeing. But if he move this part, mechanical force is applied on the film, then a light will be heard, or a light will be, then automatically horn or calling bell will be there. So suddenly it sends. So that electric signal, this movement, mechanical movement converts into electricity. That electrical signal will be converted into light or sound. So he has developed, and these are some of the articles based on that. Piezoelectric effect, we have given a last year, we got a 24, we got a patent also for this kind of work. Then rundown. So this is, yeah. So I'm truly thankful to you. Last slides of truly thankful to the research group. This you can see the heroes and heroines here. They are actually this all the work we present. Professors do not do anything, to be very frank. Professors do not do anything. All the work is being executed by the student. Professors give intellectual inputs. Jasmine is working at Sri Chitra Dirunal Institute of Medical Technology. She has developed a very beautiful eardrum hole replacement material. If some hole happens to eardrum, she made a polymer-based adhesive structure. Amala is sitting here. Where is she? It's gone out. Yeah, it's not there. And then Archana is there. Anup is working as at Indian Space Research Organization. Sneha is working in a cosmetic company. So next slide. So Megha is sitting here. She is also working on a biocomposite system. Gobika is just back from Indian Space Research ISR. She was for a training at ISRO for 1 year. Now she's another 45 days she is going there. Naja is working on a biocompatible system, polylactic acid system, blended system, and reinforced system. Amrita is completed back-to-back 2 papers she published now. Where is she? Amrita and Sneha is there. She also, her first part of her work is now Sneha is there, published. So I'm extremely thankful to these people as individuals, as my students, as my relative. We do not have any other partner. They are our soul, complete. So this show is also run by them. And a big, if you join, we will give a big clap to them. Thank you. Thank you so much. And if you have some queries, we can discuss them for 5 minutes. Thank you.
Thank you, sir, for the wonderful session. Now the session is open for questions.
So, when we are doing the cytotoxicity studies of a biological system, when we should do the cytotoxicity study and when should we do the MTTSA?
We have to do in ideally we suggest all biological examinations you do cytotoxicity, MTTSA, you do hemolysis. We basically these are fundamental examinations. It is not wise to exclude any of this. Ideally, we in all in vitro examinations, some standard protocols are there. Ideally, we do all experimentation. Do not skip anything, because for a specific, even if for a specific application, ideally you do that because the substance should not block blood flow, it should not block cell growth, it should not cause any irritation. All these things could be derived only from all the fundamental examination. Your question has very high relevance, so ideally go for all examinations.
Any other questions?
Sir, and the second one, how the drugs get anchored on the foam?
That's a good question. The pores, it exactly fits. It exactly fits into the pore, and that's the advantage of in situ making. So this during making, in situ making, during we are spreading it. So that is clutched on the. If you do it separately, it will not function. So the processing strategy has the key role there.
So you are loading metformin while during the in situ formation of the matrix blend itself.
No, no, no. Blend up. Normally, drug is added later only. After evaluation of the pore sizes, etc., drug is loaded. You can dip into the drug. Normally, you can load it. Manufacturing type, because if you subject it to some, there are some strategies somewhere we do it, but if you do that later, if we subject it to some thermal operations, drug will be killed. So depending upon, ideally you can do both ways, but no, ideally depending upon the application, you have to do that. But we have done after making the membrane, we have loaded drug later.
Also, targeted drug delivery means will it go to the corresponding organ
Specific, because drug is there are some receptors. There are some receptors. The modulation of the drug is done in such a way that that will be specifically targeted to the system, and that's called the sensitivity. Sensitivity is controlled. Mechanical triggering can be there, pH triggering can be there, the chemical triggering can be there. So specificity is being generated by different strategies.
So I mean, how you characterize it? Really injecting into a human body? I mean,
That we are not permitted to do that, but we can generate such ambience outside. So and we can do the examinations outside. GSK, once I had a discussion with the GSK Glaxo research group at London. So they said that a drug is actual experimentation with all these in vitro, in vivo examinations, and actual trial on humans. It will have only a drug will appear into the system will appear into the market only after 10, 12 years. It happened only for corona. During corona time, people could not wait that. Only for corona drugs, this kind of long experience. But all other drugs are being introduced into the market only after 10 years. Please.
Sir, how can we study this drug release?
Drug release is studied by UV visible spectroscopy. UV visible is because when the drug gets released, the concentration changes. Concentration changes can readily be observed from UV visible spectroscopy.
And also, sir,
Periodically, you can withdraw into what medium? Buffer medium. Into the medium, it releases. You can examine the medium and you can predict the concentration because you know the law, Beer-Lambert's law, you know. Based on that, it's a concentration dependency. So you can readily find out.
sir, and also, you just make this PLA with gelatin
Ah.
and purchase this metformin.
Okay.
Directly mixing or
Drug.
yes, sir.
But it's a form, so it can readily absorb. Matrix is polar, drug is also polar. So polar drug will be getting trapped into the membrane very readily.
After mixing this PLA and gelatin,
That's what she also asked. You can do that in multiple ways. That is what I said. We can do it in different ways. We have tried after making the pore size evaluations, etc., etc., etc.
which one is best?
For optimization, etc. If it is a fresh drug, fresh system, always make the matrix, characterize it properly, then only load the drug, because otherwise drug will, in evaluations, your drug will be interfering. Therefore, make the system characterize and load the drug later. Or during, if the manufacturing itself, in situ loading is possible, but we should be more careful because the polarity of the solvents, different solvents will be employed, temperature sensitivities could be there during processing, so that will kill the drug. Some of the active sites of the drug will be killed. Therefore, that should be done with that slight care. Good question.
How does the degradation time of PLA in soil compare to industrial composting?
Compared to
Soil to industrial composting.
composting. So degradation of PLA, how it can be compared to composting? Good question. Composting, we all conventional composting we do at home. No, conventional compost formation happens right from 7 days to one 1 month. The compost will, the black size will be formed. That's fully biodegradable. So PLA may take more time. We have not made a comparison between the composting, but from the data available from this system, PLA will degrade not in 1 week, but degradation will start in 1 week. But the complete 98% of the degradation happens only after 28 days, 1 month. Composting could be faster. But this is 28% compared to other. There, the comparison is more logic when it is compared with other plastics, polyethylene, etc. Compared to other plastics, this degradation is quite fast. So it is 28 days are acceptable for an industrial operation, biodegradability. No. You want to say something? No. If coir fiber. If you put coir fiber in,
environmental condition attack ചെയ്യാനൊക്കെ അത്യാവശ്യം ടൈം എടുക്കും. പിന്നെ PLA degradation ഒരു ടെമ്പറേച്ചർ ഒക്കെ ഉണ്ട്.
ഇല്ല, ഇത് സോയിൽ ടെമ്പറേച്ചറിലാണ് ഡിഗ്രേഡ്. ട്രിപ്സിൻ വെച്ചാണ് ചെയ്യുന്നത്. ആ എൻസൈം
കണ്ടീഷൻ അറ്റൈൻ ചെയ്യാൻ എനിക്ക് കുറച്ച് ഡിഫിക്കൽട്ടാണ് എൻവയോൺമെന്റ്സിൽ.
അതാണ് പറഞ്ഞത്. ജെലാറ്റിൻ ചേർക്കുമ്പം വെറും PLA അല്ല നമ്മൾ ട്രൈ ചെയ്യുന്ന സിസ്റ്റം, ജെലാറ്റിനോട് ചേർത്ത സിസ്റ്റം. ജെലാറ്റിൻ ഈസ് ഹൈഡ്രോഫിലിക്, സോ ദാറ്റ് വിൽ ബി അഡാപ്റ്റിംഗ് ടു ദി സോയിൽ എൻവയോൺമെന്റ് മോർ ഫാസ്റ്റർ. PLA മാത്രമല്ല നമ്മൾ അതുകൊണ്ട് ഇറ്റ്സ് എ ഗുഡ് ക്വസ്റ്റ്യൻ. PLA നമ്മളൊരു മെട്രിക്സ് മോഡിഫിക്കേഷൻ ഒരു അഡ്വാൻറ്റേജ് അതാണ് ചെയ്യുന്നത്. നമ്മൾ ആ സിസ്റ്റം മോർ ഹൈഡ്രോഫിലിക് ആക്കുക ചെയ്യുക. PLA മാത്രമാകുമ്പോഴത്തേക്ക് PLA ഡിഗ്രേഡ് ചെയ്യും, ബട്ട് ഇറ്റ് ടേക്സ് ടൈം. വിത്ത് ജെലാറ്റിൻ റിഡക്ഷൻ ഇറ്റ് റിഡ്യൂസസ്. അതായത് അഡാപ്റ്റ് ചെയ്യാൻ വേണ്ടിയുള്ള ഒരു കണ്ടീഷനിലേക്ക് പെട്ടെന്ന് PLA ഇത് ഓൾട്ടർ ചെയ്യും. യാ.
Any more questions?
You have some questions? Fine. So thank you. So thank you for the patient listening. Hope you enjoy the session. Thank you very much. Take care. We will be having, please, we request all of you to part. Have you completed the feedback filling? So do that. That's very important, because when an exercise is done, whether a validation happened to you through this program, because when we conduct a program, the program does not happen one day. It happens over months of efforts, etc. So whether we should know whether the effort we have taken fruitful, or right. So that is more feedback is or some corrections if in the case of food, in case of your accommodation, in case of your content delivery, in case of our courtesy to you, all these things, if anything is to be improved, we will do that definitely. Thank you.